Okay, everyone. Hello. It seems like we're online already. So let's first check the connection. And please, if you see us and hear us, could you please type something in the YouTube chat on the right? Something like loud and clear. Thank you very much, Guru. All right. All right. Thank you, Dmitry. Okay, so we're good to go. Again, good afternoon to everyone who is watching us from the southern regions. Hi, Samir. Very nice to have you with us. My name is Vladimir Krychevsky. My beautiful co-host today is Lisan Sarmashova. Lisan, hi.
Hi, Vladimir.
How are you doing?
I'm fine. Thanks for asking. What about you? How are you today?
Thanks. I'm also fine. Life is beautiful and amazing. So we are after college today, and we are back with our series of online webinars. It's been a while. We kind of missed you guys. I hope it's going to be more regular. And today we have a very interesting topic to discuss with you. But before we start, I would just like to remind you how it works. So we are now streaming from through YouTube. There's a chat on the right on the YouTube page. And whenever you have a question during our presentation, for example, you can just type your question in the chat. And then later, as we finish our slides, we will go to your questions and try to answer them one by one. If you're watching it in record, then there is still a possibility for you to pose a question. Somewhere below there, probably in the comment section, you will see the link to our forum on NAFTA College website, where we can continue communicating, and you can address all the questions you have, and we'll try to answer them offline. Okay. So now I think we're good to go. I would probably ask Lisan to share the slides, and we will start. All right. So the topic of our discussion for today is evaluating efficiency of multilateral producing wells in bottom water drive reservoir with a gas cap. It's been a very complicated job. It actually involved working with several different technologies, comparing the results. That was quite interesting. That lasted for more than a year, actually. And the results of this job were also presented on the Russian SPE conference last year. So down the slides, you will see the reference to the paper that you can actually download on onepetro.org. All right, so let's move on. Let me just tell you a few words about an object that we actually studied. So we have a field. The field is located in Western Siberia, in the north of it, actually. The field is quite remote, and there are still some doubts about the way how to develop this field full scale. So the field is still in the appraisal period. The oil company is trying to drill different kinds of wells to see which one would be the most efficient and economical. Actually, they had several vertical appraisal wells, which were retested several years ago. Then they drilled several horizontal wells, and one of them was quite long. Actually, it was about 2 kilometers. And on that stage, we also participated in a study project. We had the DTS, we had a pressure monitoring, and hence we had some preliminary estimates of reservoir properties. And we had some predictions on completion efficiency, different completion efficiency. But a couple of years ago, the oil company decided to drill a very technological wells. One of them was multilateral. Another one was a fishbone, also multilateral well. And the concern they had is that they didn't have any liners in the sidetrack. And the concern was the collapsing of the boreholes in the sidetracks. And they were afraid that they would lose the productivity index of the wells with time. And they wanted to monitor if it happens, and if it is, I mean, how severe it is and how it affects the productivity of the wells. That was one of the concerns. Another concern was the gas, because as it says in the name of the topic, just above the oil bedding, we had a gas cap, and we actually also had a free water level beneath our wells. So it's an oil rim. It's not very thick. I would say it's from 8 to 12 meters in different zones. And there was still a risk that we would have a gas breakthrough during the production. Another problem that we had, and it was actually a problem for our study, that as the field is still remote, there's no pipeline, and we didn't have the possibility to produce for a long period of time. So each of this well was scheduled to produce for about 8 months. And all our study should be fit into this 8 months. And for such a well, it's actually, well, it's quite a challenge. So here you can see the goals and objectives, which we tried to achieve during the study. We need to support the selection of the most efficient completion of the well. And also we needed to confirm our previous estimations of reservoir properties and the efficiency of well reservoir contact in these wells. And also the objectives were to assess the risks of gas breakthrough, lateral boreholes collapse, well, and again, assess the properties of reservoir in the well. So here is what we were trying to do. Now let's see which technologies did we have in our at our disposal. So first, we had a DTS. So each of these wells were equipped with the fiber-optic DTS cable, which was placed in the borehole, in the main borehole, and it was actually placed in a full well up to the very toe of it. So we had the possibility to get a temperature profile from the whole well bore at any moment of time. Then, of course, we had a bottom hole pressure monitoring. So we had an online pressure gauge, which was located near the pump, and we could monitor the bottom hole pressure, again, during the whole appraisal period. And also, we had memory gauges, which were placed in the horizontal section on the well. Each well had 5 memory gauges. And then as we extracted the completion, we were able to read the data from the gauges and then do something with this. And that's another, actually, in my view, it's a unique part of this study, which Lisanne will tell you about a bit later. All right, let's move on. First, let's start with the DTS, so distributed temperature sensing. So how it works and what it brought us. So let's first try to remember what are the main temperature effects in a well. So we have, well, let's look at the top left picture. The main temperature effects would be throttling. So whenever we have fluid coming into a well, it warms up. If it's a gas, it cools down. Okay. Then, as the fluid moves along the borehole, there is a heat exchange between the moving fluid and the rock outside the borehole. That's a heat exchange. And then, of course, when the fluid moving along a borehole meets another fluid which just came into a well, there's mixing. And the temperature is being mixed between these two fluids. That's quite easy. So that is actually a picture for a vertical well. Down here, you can see the same plot for a horizontal well. And if we have the zones, particular zones of inflow, like, for example, in a well with a multi-stage frac, then the picture could be like this, like down here. And that's actually a bit easier because we have these dedicated zones and we have a huge inflow from small particular zones of the borehole. But in many cases, we do not have fractures, like in this case, for example, we do not have any fracs. And we have a huge borehole. It's more than 2 kilometers long. And everything flows. And in this case, we might get a picture like on the right, where we have several layers right next to each other, and each layer is contributing. And this picture is not as well as contrast as you might expect. And the methods of quantification of the inflow could fail you, unfortunately. I mean, the simple methods could just fail you. Because if you have different situations, like layers, one of them with high contribution and high thermal conductivity of the rock, and low contribution with a low thermal conductivity of the rock, the pictures could actually look the same or very, very similar. So the main problems of conventional temperature logging in horizontal wells is that the temperature changes in a horizontal well bore are very low compared to the vertical one. And also, usually in a horizontal well, we have a lower pressure drop. And the inflow from a meter of the borehole length is, well, an order of magnitude less than in a vertical well. And that's why all our temperature anomalies would become, well, barely visible. Okay, now let's move on. I'm going to just show you several examples on how it works. So this is conventional temperature logging in a vertical well. Here you can see the very nice picture, the temperature panel on the left. You can see the contribution of several layers, and you can see the throttling and then heat exchange and then mixing. You can actually see all the reservoirs which are contributing. And if you have a temperature simulation software for a borehole, you can actually even quantify the inflow based on this temperature logging. And it would perfectly agree with the estimate from the flow meter that we also have in a panel somewhere in between of this plot, right? Okay, so this is what we are used to in vertical wells, but let's move on. And here we see what is a usual picture in a horizontal well. So it is a horizontal well. There's no fracs in this well. And on the temperature panel, you can see that there are no major anomalies in the temperature. And basing on temperature only, that would be very, very hard to distinguish and understand which intervals of the well are contributing and which are not. So as a matter of fact, here, with this conventional temperature logging, we needed additional information. And well, thankfully, in this case, we had the spectral noise logging. And in this panel on the right, you can see that we have a noise indicating the intervals of the inflow. And with this additional information, it is actually possible now to interpret the temperature profile in terms of inflow contribution. All right, so again, this is a conventional production logging where we just, you know, put the gauge in a borehole, run it up and down several times, measure the static, then start to producing, then shut it off, run several additional measurements. So it's a conventional way of doing it. So what is different with the DTS technology? With the DTS, we always have a gauge in a well. So I will just remind you that the fiber optic cable located in a well is actually a distributed temperature sensor. It is actually also an acoustic sensor. But here in this study, we only use the temperature sensing. So it means that anytime we can measure the temperature at any point of the fiber optic cable. That means that we may always see the full picture of temperature distribution along the wellbore. And that is actually very good. But in order to understand the inflow contribution, we would still need, of course, to change the flow of a well. Change chokes, shut it down, start the production. So we would still need to create some temperature anomalies. But what is much easier is that we do not need to run the gauges down. We don't need to think how to make a well flow while we're doing the production logging, because the well is just flowing with the pump, and we always measure the pressure. And that is a giant plus of DTS technology. All right, so that was just a small intro. Let's move on. So here you can see the actual data from the DTS which we had on this job. We will give you examples based on one well which we studied. It's a multilateral well. The schematics of the well you can see here on the left, multilateral well 1. And this dotted white line in the main borehole is actually showing the location of fiber optic cable. So on this plot, on this slide, you can see the temperature versus time on different depths. So the orange line, which you can see on above, is a temperature somewhere above the pump. It actually indicates how the well was operating. So it's been, let's see, idle at first, then it produces the orange fill, and then again it's idle, it's first shut down, the blue filling, right? Okay, so the gray line below actually shows the surface temperature. So we had a part of the DTS cable which was located on the surface between the well and the station which actually registered the temperature. And we can see the temperature. You should use the left scale. So you can see it was in the summer. And yeah, it was quite warm in the day. It was more than 30 degrees and quite cool in the night. You can see, well, 12, even as low as 10 degrees in the night. So we had a huge temperature fluctuations on the surface. And unfortunately, it affected the downhole measurements. So the other curves on this plot, the lowest pack, you see there are many curves. These are the measurements of temperature downhole at different points of the horizontal wellbore. But you can see that this fluctuation that we had on the surface actually affected the measurements downhole. And it is, of course, very bad. It's, of course, it's impossible. There could be no temperature fluctuations downhole. So that is actually an error of the measurement with DTS. That's because the surface part of the DTS cable should be always properly insulated. And unfortunately, it didn't happen on this study. That didn't create us very huge problem with this well. But that is a moment which I would like to highlight, that because if you're using a DTS, it's a very expensive technology. And I mean, if we're doing it, we should do it right, of course. But still, we can see here that when we produce, the temperature is going down. I mean, the temperature downhole is going down. You can see the whole pack of colored curves going down. And then once we shut the well starts warming up just a bit. You can see it on the right scale that the pressure temperature variation here is like, I don't know, maybe only a half of a degree in total, yeah, which is quite small. But still, that's information. So we had these temperature measurements at different parts of the well bore, which actually allowed us to estimate the inflow. Let's move on to the next slide. So here we're showing you the technique, how we did it. So this well had some gas in production. There was some free gas coming into a well bore, and hence, during the production, the well was cooling down. Then when we shut the well, it warmed up. And how to estimate the inflow profile? Let's see. Whenever an interval of your well bore is, let's say, producing, it's cooling down. The rock around this zone is also cooling down. And then when you shut the well is starting to warm up, but the intervals which contributed the most would warm up slower comparing to the other ones. Well, I think that's rather simple. So if we have in the history of the well different time periods when we started producing, then shut down the well, then start producing again. So then by temperature variation and by the speed of this temperature variation at different zones, we may estimate the inflow contribution. So here on the right, you can see the formula. So we were using this normalized temperature relaxation coefficient, which gave us the information of the inflow contribution. On the left, you can see the plot, the heel on the left, the toe on the right. The green lines below are the locations of the side tracks. And this purple filling in the bottom panel is actually our estimation of the inflow. So here we see a huge inflow from the side tracks, most of the side tracks, and also the main well bore down to the toe is also contributing, and there is an inflow that we can actually see in this panel. All right, so that was our methods of interpreting the DTS data. Now let's move on to the next slide. We actually had two buildups during this whole appraisal production period. We had two buildups, one in the very beginning of production and one at the end. And each of these buildups actually provided us with the calibration information to use this normalized relaxation coefficient technology. So we had two independent estimates of inflow profile by DTS. So here you can see the picture on the left and on the right. You can compare it. The panels below are actually showing the contribution. And if we look thoroughly, we may see that during these several months of production, the inflow redistributed a bit. And we now have more inflow from the main well bore comparing to the side tracks. So, well, I think that's pretty natural, of course, because the side tracks are starting to interfere, and some of them are, of course, losing the production. The pressure is going down faster for some side tracks, and that's actually okay. But the main well bore starts to produce a little bit more by the end of this appraisal production period. Okay, so these would be the results of the DTS. Let's move on to the next technology. We also had a pressure monitoring. And we were trying to use the PTA methods to estimate the reservoir properties and the completion efficiency, but also we needed to understand if we have this lateral borehole collapses. So we needed to find a way to see if we are losing the effective length of the well and its productivity index. So now let's move on to the next slide. We used the Polygon software to simulate and then interpret the data. So here you can see in a picture on the left, the schematics of the well. And here on the right, you can see our design. So in order to understand what we can actually see on the actual test, we needed to properly pre-design this test. So we knew from the previous studies that the permeability that we're dealing with is very low. Very low. So dynamic permeability, I mean, accounting for relative permeabilities would be, well, probably close to 1 millidarcy. Also, the well itself is huge, huge. So, I mean, the total length of all boreholes is, even if we had a pressure buildup for all 8 months that we had, unfortunately. So we needed to find a way to understand what is the dynamics of effective length through time. And we had the idea that okay, the permeability is low, and at first our well should behave like a simple horizontal well before the laterals start to interfere. And the first flow that we see in a horizontal well is the early radial flow, which is like a radial flow around the borehole. And the time of this flow actually is from approximately 10 to 100 hours. That was our estimate from the previous study that we had. So we do not need to do a very long pressure buildups in order to see this flow. And this flow actually depends on horizontal permeability, vertical permeability, and the effective length on the well. And well, considering the permeabilities should stay the same, right? If we see the dynamics of the early radial flow, we would be able to estimate the changes of the effective length. That was the idea. So we put this in a model. We simulated the production for several months, several short buildups, and somewhere between these buildups, we just collapsed some boreholes in order to see what we will see then on the buildup. So here you can see an axis on the right plot. So the first X is just we collapsed one borehole in a model, and then between PBU2 and PBU3, we collapsed another 2 boreholes. Okay, and now let's see what we got as a result. Could you please click on a slide? Right. So here you can see the plot on the right with a log for all these buildups, 1, 2, 3, 4. And we can easily see that this early radial flow, which is filled with the green color, is changing. I mean, the position of the derivative is shifting up. And of course, the higher effective length that we had on the first buildup shows us the lower position of the derivative. Then once we collapsed one borehole, we move up to the orange derivative. And then once we collapse another 2, we move even higher to the blue and the dark blue derivative. So this way we just ensured that, yes, I mean, even theoretically, by design, we are able to see this collapse if it happens. Okay, so that was our design. Let's move on. So here we can see the actual result. This is the pressure monitoring results of this well. We can see that we started producing somewhere the end of July, and then the final buildup ended in the February. So we only had several months. We have a pretty nice buildup in the beginning, a very nice buildup in the end. And also, of course, we did monitor the pressure through all the time. And then what did we do? We just matched the model of this multilateral well to the first buildup. And then once we produced and produced and produced, and then at some point in time, the bottom hole pressure reached some limit, which I think is actually, it's due to geomechanical reasons. At this point, we see that our prediction which is in red here, shown in red, right, starts to gain discrepancy with the actual data, which are blue dots. And the last buildup is actually, well, it's the same. I mean, in terms of the reservoir pressure, it's the same, but in terms of productivity, it's very different. So we see that there is a productivity loss. A small productivity loss could be seen just from this plot, and we can actually see where it started, and that gives us an idea on what would be the minimum safe pressure, safe bottom hole pressure to produce from such wells. All right, now let's look at the log diagnostics. So the plot from these two buildups is on the right. And here we see this vertical shift, which I've been talking before. So the first buildup is the short one, and it's a lower red derivative. And the second buildup, you can see it's longer, it's also red, and it's located a bit higher than the first one. So in fact, we are losing the effective length. We are losing the productivity, but now we can quantify it. Because the position of this radial flow actually accounts for the total horizontal length, and we can estimate it and then see, I mean, is that a severe problem or not? And in this particular case, we actually lost less than 10% of the total length of the well. So now we have a direct information on what to expect if we drill many wells like this, what would be the order of magnitude, let's say, of this collapsing problem, and when it occurs. So I think that was the main result of this pressure monitoring. Also, we were expecting to have a linear flow just as this early radial flow ends. But due to an expanding gas cap just above our well, we do not see it. And instead of the linear flow, we see a radializing, a further radializing of the flow, which actually means the support of a gas cap, which was another important conclusion from this pressure study. All right, I think this is it for the PTA. And now I think we can move on to the last but not the least, very interesting part. Lysan, the stage is yours.
Yes, thank you, Vladimir. Can you hear me?
Perfectly.
Yes, okay. Let me present my part of the presentation. We'll talk about multi-gauge pressure loss monitoring with an example of multilateral well. So for wells with complex completions, it is possible to obtain an alternative estimate of the inflow profile. To achieve this goal, we set the following tasks: pressure analysis, data calibration, and estimate of the inflow profile. As Vladimir mentioned, the well had 5 memory pressure and temperature sensors that pass 20 m located in the toe and near each lateral. Combined with a pump gauge, this provides 6 pressure recordings along the wellbore. The location of Z-pass tools in well is shown on the slide. So after the end of the test and the extraction of the completion, the data from the sensors were read and analyzed in the Polygon software. A bit about pressure loss calculation. It is known that the difference in readings between sensors is the sum of 3 values. Difference in absolute depth of sensors, difference in absolute error of sensors readings, and friction pressure loss due to fluid flow. From the point of view of estimating in the inflow profile, the main component in this formula is pressure losses. Since they quadratically depend on the average flow rate in the well bore between the sensors and linearly on the distance between them. Since the expected pressure losses are comparable to the absolute accuracy of the gauge according to their specs, DP values cannot be directly used even after correcting for absolute depth. Differential pressures need to be calibrated, and the best opportunity for this is to use the data recorded during the well shutdown. After the well is shut down, there are two processes that affect the pressure difference between sensors. Firstly, a sharp decrease in the flow rate and a drop in friction pressure losses. Secondly, redistribution of fluids, that is ascent of oil and immersion of water. Since the first process is rapid and the second is slow, after a short time after shutdown, in this case about 30 minutes, pressure losses disappear, and the redistribution of fluids still does not significantly affect the relative readings of the gauges. A calibration of the relative readings of the sensors at this allows leaving the error of the instrument and the difference in absolute depth out of brackets and calculating only pressure losses during the well production. With this in mind, to calculate the profile, 2 times intervals were selected, located immediately before the shutdowns, which were used to calibrate the sensor readings. So let's take a look at the calculation of the inflow profile for these 2 intervals. The slide shows the result of the sensor calibration in the analysis interval. The calibrated differential pressure values for adjacent pairs of sensors were divided by the distance between them. It can be seen from the plot that the specific pressure differences are logically arranged in ascending order from the well toe to the pump, since it is in this direction that the flow rate increased. So after that, the total flow is calculated under the following assumptions: uniform flow, uniform inner diameter and tubing roughness, and the flow rate is known from surface measurement. The calculation results are presented in the table. In this way, we see the contribution of each lateral to the total well flow rate. Then, in the same way, the calculation was performed for the second interval, for the second PBU 4 months later. We see that we have slightly different values in the table for the total flow. This is due to the fact that in 4 months, the inflow was distributed among the lateral. By the difference in the total flow in the zones between the toe laterals and the pump, interval inflow from individual zones is calculated. The table shows a comparison of interval inflows % at the beginning and at the end of the appraisal production of the well. So I have to admit, when evaluating the interval near the first pressure buildup, one of the sensors was excluded from the analysis due to problems in the reading. Therefore, one of the inflow estimates was given for 2 intervals in total, the interval from the toe and lateral number 4. In the plot on the left, this estimate is divided in halves. So based on the results of calculating pressure losses on the example of multilateral well, the following conclusions can be drawn. The main contribution to the inflow at the beginning of production was provided by the lateral number 3, about 50%. The main contribution to the inflow at the end of the research was provided by the well toe and the lateral number 4, about 50% too. The losses of the working length recorded by the PTA during production occurred most likely in the lateral 1 and number 3. Around 3 times decrease in the share of inflow is observed in them. So finally, what I want to say is the conclusions from the analysis generally confirm the conclusion from the DTS analysis on the redistribution of the inflow from the heel to the toe with the time of production. That's all, Vladimir.
Thank you very much, Lisan. Pretty comprehensive. All right, so now let's probably sum up results and conclusions. So you can see that this study was really complex. So we had several technologies to use. We had constant pressure monitoring online. Also, we had online temperature sensing. And also we had this unique opportunity to give an independent estimate of the flow contribution after the end of the test when we had our memory gauges on the surface. So I find it rather interesting. And now let's just try to sum everything up. So we have two independent estimates of the inflow contribution, one from DTS, another from the pressure loss calculations. And they actually agree. And we see that the contributing parts are not located in some particular zone. Sometimes, we can sometimes hear that, well, in a long horizontal, only the heel part works. But no, not in this case, at least. So we can see that there is some distribution of inflow and actually changes through time. Well, which is quite logical if the pressure is changing as we produce from a well. So we actually see that the distribution changes again from the heel part and then to the toe part slightly as we produce for several months. Okay, let's go to the next conclusion. We have this constant pressure boundaries near the well. So I already see the question in the chat how you concluded the gas cap support. So let's see. If we have a horizontal well, let's just think about this well for now just as a simple horizontal. We have this early radial flow, which should be followed by a linear flow. Because once the pressure distribution reaches the top and the bottom of our layer, these boundaries should, in a conventional model, be sealing, and then the pressure starts to redistribute, and the flow gets linear, just perpendicular to the wellbore. But we do not see any signs of a linear flow. Actually, we expected it because, in fact, we did the study in this same field of standard conventional horizontal wells a year earlier. And we knew that we would be expecting the support from a gas cap. So here we can see that we do not see any sign of a linear flow at the end of this early radial one. And that can only happen if we had a huge thickness of the reservoir, which is not true. And we can see it from the open hole log clearly. And the only other reason is the pressure support from either a water drive from below or a gas cap from above. And in this particular case, there were more energy in the gas cap. And we believe that the support, the pressure support that we see, which makes the derivative radialize, is actually a support from a gas cap. Okay, but also another conclusion which could be drawn from this test is that during the whole study for several months of production, we did not see any sign of a gas breakthrough. So I will just remind you that if we have a gas breakthrough into a well, of course, we would see it by GOR measurements on the surface, but also we would be able to see it downhole with the DTS. Because once you have a gas breakthrough, there would be a huge negative temperature anomaly somewhere around the location of this gas breakthrough. And we did not see anything like this. So it's actually good news that for, well, at least half of a year, we would not expect any fast gas breakthroughs. All right, and the next conclusion, the last actually, is that yes, unfortunately, we do see a moderate loss of a total working length. So it seems like somewhere in these lateral boreholes, we do see a collapse. But again, comparing to the total working length of the well, it doesn't seem critical. And we see that we only lost about, well, from in one well, it was about 8%. In another well, it was about 13% of the total working length, which of course affects the productivity, but again, not critically. So also, as we had this pressure monitoring, we estimated the critical pressure where the productivity starts to decrease. So it means that we may now have some ideas we can correlate to what geomechanical engineers say, and then together come up with a perfect balanced bottom hole pressure value that we can use for the prospective producers. So I think that all of these findings are quite important, especially when you're trying to plan the full field development. You are trying to choose the most effective way of completion. You're trying to re-estimate the reservoir properties as you really need to know your production profile in order to calculate the NPV. And I think that this particular study has provided a lot of important inputs in the process of field development planning. So I would just like to say a couple of words. So, I mean, if you have similar tasks, if you have similar problems, or you want to try similar techniques, then you are, of course, welcome to contact us, because this particular study was extremely interesting for us. Because again, it's a very complex study with different kinds of technologies and a lot of work. And that is something that actually drives us, you know? So, I mean, if you are seeking for some advice with the similar problems, you are most welcome to contact us anytime. I think we're out of the slides, are we, Lisan? Yes. So now we would just say thank you. Thank you very much. And now let's move to your questions. All right. So I already see several questions in the chat. So a question, how long does Z pass installed at the well? Okay, which depth and temperature? Okay, so ZPass 20M is a quartz member gauge. And in this study, we had 5 gauges in a well bore. The gauges were set down for the whole appraisal production period, which was about 8 months, I believe, 8 months. So all of the gauges endured, all of them actually recorded a very nice pressure. You saw it in the slide of Lisan. And as to the temperature and the pressure, so the depth was, well, a little less than 1 kilometer, the absolute depth. The pressure was, well, about 80 bar, and the temperature was about 35 degrees Celsius. I think that does it. Okay, I have another question. So how you concluded the gas cap? Yeah, I was trying to answer this question during the presentation. It can be due to the limited drainage area of each branch of well, can it, right? In case of gap, increase in the delta P. Right, so, okay, so the, whenever we have the limited drainage area of each multilateral, yeah, I'm just trying to imagine the situation. That would mean that our boreholes our side tracks would not actually interfere. We will have a limited zone for each lateral, and then the pressure derivative would go down. Yeah, probably that's true. I think that's true, but again, that's very hard to imagine, because I mean, basing on what we see from the drilling, from seismic, and actually from pressure monitoring, we do not expect to see any boundaries around the well or, of course, between the laterals. So, I mean, theoretically, it probably could be possible to obtain a similar picture on a derivative. But I mean, it can't in any way relate to the geology of this particular reservoir. And in the case of gas cap, you expect an increase in delta P. Now, in fact, the pressure support would cause a decrease of the derivative on a buildup. So it's like a common picture. Whenever you have a water flood, or you have a water drive or a gas cap, in all these cases, the pressure support would cause your derivative to drop, or as in this case, at least to radialize instead of going up linearly. Yeah, so I think that's the most probable, I think 99% probable explanation for what we see is a gas cap. You mentioned about polygon software. Which part from the study? Right, so Polygon was used for all 2D simulations, which we preliminarily did for the test design. And also Polygon was used for interpreting the results. So Polygon is a comprehensive tool which allows us to run PTA, RTA, and also this calculation based on the friction pressure loss also is implemented in the Polygon software. Thank you. All right, guys, seems like we're out of the questions for now. Let's wait for, I don't know, 10 seconds. See if you have any new questions. Again, if you're watching it in record and you have a question now, you can address it on our forum. So there will be a link somewhere on this YouTube page, probably in the comments section, and you will be able to address the question offline, and we will be happy to answer this question. All right, so I think this is it. I want to thank you all guys for attending. Again, we missed you, and it's been a while, and I hope to see you soon again. I welcome all the participants. If you have something interesting to share, if you think that you have an interesting study which you would like to share with the community, please, you are very welcome to contact us, and we will give you the stage of the SNAFTA College webinars, and you will be able to present it. We will be your hosts, and it will be very smooth. And I think everyone who participated in our webinars was pretty happy, right? Okay, and now, well, I think it's time to say goodbye. Thank you very much again. Please be safe. Have a nice day. Lisanne, do you have anything to add?
Yes, thanks to NAFTA College for opportunity to participate this webinar, and hope to see you soon. Have a wonderful day.
Sure. Lisanne, and thank you very much. You helped a lot. Okay.
Bye.